Hello and welcome to the Kavli Foundation Spotlight Live webcast on the recent big discovery in cosmology. And of course I'm talking about BICEP 2. Now while BICEP 2 has not risen to the lexonic stratosphere like the Higgs has, I believe it will. And I want to read a quote here. Last week Bill Foster, who is a congressman from Illinois and one of the two physicists in Congress, had this entered into the congressional record. This discovery by the BICEP 2 team has been globally recognized as one of the most important fundamental breakthroughs in science in our lifetimes, a landmark of American academic achievement that will live on in the science textbooks forever. So it's a big deal, and what we plan to do today is talk about why it's big, what actually was discovered, and have a good time with this. So a month ago, the BICEP team awed and shocked the world of cosmology by announcing that their South Pole telescope had detected a cosmic fossil from the earliest moments of creation. And to be very specific, just to stretch your minds, if everything is as we think, it comes from 10 to the minus 38 seconds after the beginning, and I won't even try to bother to say 0.00000. And so that's the big thing, and that's the thing we're going to be breaking down for you today. So I'm Michael Turner, and I'm your moderator for this. I'm a cosmologist and director of the Kavli Institute for Cosmological Physics at the University of Chicago. And I'm joined by three experts who can describe this exciting result and help us understand its significance. John Carlstrom is also from the University of Chicago, and he's the deputy director of the Kavli here, and he leads the South Pole Telescope Project, which has also been involved in looking for this signature from inflation. Walt Ogburn works on BICEP 2 and the Keck array. These are two telescopes at the South Pole. He's a postdoc at the KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology at Stanford, and he was part of the BICEP team that made the discovery. And last but certainly not least is Abby Vieregg, my new colleague here at the University of Chicago. She's a member of the BICEP 2 team, and she just joined our faculty on January 1, and she's a member of the Kavli Institute for Cosmological Physics. So John, Walt, and Abby, thanks for being here.
Thank you.
Oh, thanks.
So let's start out with just a little bit of background. We got a couple of slides to go through here, and if we can have the first slide. The first slide you don't even need to see. It's the most iconic image in all of cosmology. It's the Hubble Deep Field. And the Hubble Deep Field is the universe that we see today. The universe that we see today, when we look at the sky, we see 100 billion galaxies expanding from a Big Bang beginning. And the Hubble Deep Field is just a tiny little bit of that, but it gives you a sense of what the universe looks like today. And of course, the challenge is to understand how we got here. And for the past 20, maybe even 30 years, we've had a guiding paradigm called cosmic inflation. And this paradigm, which builds upon the Big Bang, and is quite remarkable. It says that when the universe was very, very young, fraction of a second old, it went through a tremendous growth spurt, grew by a very, very big factor, and that things on the subatomic scale, in particular quantum fluctuations, grew to astrophysical size and seeded the galaxies that you see in the Hubble Deep Field. This is a very, very bold idea. And over the past 20 years, we've accumulated some evidence for it, but not really the smoking gun. And so for 20-some years, the theorists like myself have been saying, you know, the smoking gun for this is polarization of the first light being the cosmic microwave background that we'll be hearing more about. So you have to measure this signal. So the experimenters said, this sounds really, really good. you know, this sounds really, really big, so how strong is this signal? And the theorists said, well, that's a really good question. And the highest brow theorists, who sometimes don't like experiments, I'm talking about some of the stringy people, said, it's so small you will never detect it. And others said, well, it could be quite big. And so over the past 20-some years, there's been a joke, I think, behind the backs of the theorists like me that the theorists have sent us on a wild goose chase. That there may be a goose, there may not be a goose. And so this has been somewhat of a wild goose chase. And scientifically, of course, it's extraordinarily high high gain if you find it, but the risk is unbelievable because unlike many of the other things, you can't even predict how strong the signal could be. It might not even be there, and so that's kind of where we are right now, and that's the background for this, and it was actually found. And in order to, or apparently it was found, in order to find this signal, which we're about to hear about from Abby, cosmologists, the experimenters, had to go to the South Pole. And so it's got some adventure in it. It turns out the South Pole is one of the best sites. And so if you're looking at the slides, you can see the airplanes flying into the South Pole, and then you can actually see a picture that I like. I mean, maybe Abby and Walt don't like it so well, but it's a beautiful picture of Bicep being fed its helium in the middle of the night. And so let's see, the next slide will show this picture of what they detected, the cosmic swirls. So for right now, let's just call this swirls. So they're looking for a certain kind of polarization, and the black arrows in this diagram are the polarization. And if this looks swirly to you, you've seen the signal. And so that's what all the excitement is about. And so, Abby, why don't you tell us a little more about, you know, what you discovered, how you discovered it?
Right. So, as Michael said, we built a telescope at the South Pole called Bicep 2, and that telescope makes extremely sensitive measurements of the oldest light in the universe. So if you want to look, we look as far back in time as we can to see the oldest light in the universe, and we do this with our telescope at the South Pole. And what we saw was this pattern that you see on the slide in this oldest light in the universe, and that sort of swirly pattern actually tells us about this period of inflation in the first fraction of a second. It's the first trillionth of a trillionth of a trillionth of a second after the Big Bang. What this swirly pattern does is it tells us that the universe underwent an unbelievably fast expansion in that first fraction of a second.
Terrific. So let me just ask here. So the little the swirls, that's this polarization of the oldest light, the microwaves. And what are those colors?
So the colors are just another way of representing the black lines, actually. So the colors tell you where it's a little bit hotter or a little bit stronger, and where it's a little bit colder or a little bit weaker.
And so we're seeing this first light is coming to us when the universe is 380,000 years old.
Yeah, that's right. So the light that we're looking at comes to us from when the universe is 380,000 years old. But what we do is we use that light to actually look even further back in time at this first fraction of a second.
So the expansion, they created these gravity waves back then that then twisted around the polarization to give these swirls. And yeah. So these tiny little swirls. Now I do have to mention this because we've got people watching us, and you can tell whether or not you're a cosmologist. If you look at this picture and your heart goes pitter-patter, you're a cosmologist.
Yeah, because we're looking at a picture that's as old as we're ever going to make, right? It's the oldest picture of the universe.
That's right. And if it just looks like sort of random noise, you're not a cosmologist. Okay, so we've got evidence from gravity waves, ripples in space-time that were created during inflation, and there it is, and it's a tiny, tiny signal. So, Walt, how do we know that this isn't, I mean, if I look at this, it doesn't say I'm a gravity wave from when the universe was 10 to the minus 38 seconds old. How do we know that this isn't something? I was told by my observer friends that when in doubt, you know, seeing an astronomical result, you should ask, could it be due to dust? How do we know this is not something else between us and way back when?
Well, what the world saw when we announced our results last month is that these guys seem pretty confident now, and we are, but there's really a long process that went into making us that confident that you didn't necessarily see, and that lasted for more than a year, while during that time we were kind of our own greatest skeptics and put our own results through, I think, more scrutiny than I've seen from others so far. And there were a few kinds of things that really brought us from the point of thinking we've seen the start of a signal that may or may not be real to thinking we've actually detected the inflationary smoking gun that we've been looking for. And the first part of that is just that we accumulated enough data that we could put a number on the statistical significance of our result that's above this 5 sigma, which is kind of the goal that everybody wants to reach, to claim that they've really detected something that's not just a statistical fluctuation and it's not going to go away. So we've actually gone past that line. That means that the sensitivity of our telescope is enough that the signal we've seen is really much larger than any kind of chance fluctuation, so it seems to be something real. The second thing is to convince ourselves that it's not just an artifact of the instrument itself. And we spent a lot of that year thinking up every crazy idea we could about how the telescope might be going wrong in some way that would make a fake signal. And one by one, we couldn't make any of them actually work. We were able to find out exactly how our telescope is behaving in such a way that we could really simulate everything it does from start to end and find out that all of the properties of the detectors, of the optics, of everything else are not going to make a fake signal like this. And then to make ourselves even more confident of that, we did a second type of check by comparing the data from BICEP 2 with a second telescope that we're currently running called the Keck array, and we saw that they indeed see the same signal. It correlates between those two maps. And then again, with a third telescope that actually took data a few years before called BICEP 1. And so that comparison really drove the point home that this is not something just coming from the telescope, it's really on the sky. And then the third thing you want to make sure of is that it's actually something that's cosmological, that's from the CMB itself and not something between us and the beginning of the universe that's just getting in the way, maybe something in our own galaxy. And the best information we have on that comes from a few different places. One is just that we looked at multiple colors from BICEP 1. It had detectors observing at 100 gigahertz and 150 gigahertz. These are just two colors of microwave light. And if you see a signal in both of them, you can compare and see what, whether it has the right shape, the right dependence on frequency to be the microwave background or to be, as you said, dust or maybe synchrotron emission from the galaxy. And that analysis shows that it seems to be consistent with being a cosmological signal, not very consistent with being one of these foregrounds. In addition, we took the best information that we have about the dust and synchrotron and other signals within the galaxy and saw, can they make such a big signal? It looks like it's very hard for them to do that. And does the signal from our best models of these galactic dust and other things actually correlate with the data that we have? So we saw that our two telescopes could correlate with each other. They give the same signal. And you can do the same thing with our data in the foregrounds. And as far as we can tell, it doesn't correlate. So it looks like what we have really is a clean galactic signal. Of course, you always want to know more. And people have been coming up with all kinds of interesting ideas and further tests that we can go on and do to really...
Well, we'll get to that. Let's... you got a really tiny signal. You're convinced that the best explanation is something to do with inflation. And we got an expert here. We've got a really good critic, because John Carlstrom, my colleague, this wild goose, he was chasing it too, and he's got a big telescope at the South Pole. So let's see if you've convinced him.
Well, it's a remarkable paper and a remarkable achievement. So one thing I would like to point out is, as Mike just pointed out, a lot of us are looking for this signal, but BICEP 2 is out in head. They have reached uncharted territory in sensitivity. They have a very powerful telescope, and they've gotten to levels, sensitivity levels that have never been obtained. So they're the first there, and they're charting new territory. So as Walter said, there's a lot of things you have to figure out to convince yourself that's real. And it's such a tiny signal. We're talking about a signal that's 1/10 of 1/1,000,000th of the light we're getting from the cosmic microwave background. And of course, we're also getting light from other contaminating sources. So it's a little needle in a big haystack that they found. What we'll want to do is make sure that another team with another telescope, hopefully getting just as sensitive, we'll see the same signal in other parts of the sky as well.
So you're talking about your team, the South Pole Telescope, might be?
That'd be a great team to do it right away. Sure. We're trying, and in fact, we're looking at the same skies. So we will test a lot of the measurements. We actually, hopefully, we can cross-correlate with them. But it'll be important to also measure other parts of the sky as well. But it's a remarkable achievement, and I would say it's like having a you can build a very powerful telescope, and then you have to have a very good driver, and a very powerful car, let's say, to run a race, but you need a good driver, you need a pit crew, and they had the whole thing. They had a real winning team to do this. It looks very good.
Well, we'll come back to, Carl Sagan was fond of saying extraordinary results require extraordinary evidence, and I think this is an extraordinary result, and we'll come back to what do we need to do next to really check every possible thing. But let's talk about the implications. So here we have this signal that its best explanation is that this is the imprint. It was caused by gravity waves that were produced when the universe was 10 to the minus 38 seconds old, and that's apparently what it is. What does that mean for cosmology? What does it mean for humanity? What does it mean for fundamental physics? Anyone want to bite on that one?
Well, I'll give a quick answer. This idea, it ties together what we know about the very small, in fact, even smaller than what we know about, but that there's quantum mechanics and uncertainty at the fundamental level. And this is saying that uncertainty somehow generated our entire observable universe. And to me, that's just incredibly profound. It's amazing.
And our universe back then, we're talking about, there's so many amazing things about this, but everything we can see today, that Hubble deep field that's unimaginably large, at this time when the universe was inflating, everything we can see today occupied a size smaller than a proton. Yeah. And so that's stunning. Actually, does this rule out any of our theories of the? Is there somebody who's inflation's a big winner so far? Anybody a loser on this?
Well, I don't know if anyone else wants to join in. There is a theory, our universe is expanding, collapsing, expanding, and it's an ongoing cyclical nature. And at least proponents of that theory have said you would not detect detectable gravitational waves in the polarization of the cosmic microwave background. So that theory, I imagine, is under quite a bit of stress right now.
Mm-hmm.
So that was, if I can chime in as a theorist here, one of the things that inflation was so successful, such a dominant paradigm, that myself and some others were saying we need a competitor, because in science, just like in athletics, if you have two people who are pushing, or two theories that are challenging one another, and so this cyclic universe, the bouncing universe, was a challenger, and then you have to have discriminators, and they were quite proud to predict that no gravity waves. So I think that's right. Anybody else want to weigh in on the significance? I mean, Abby or Walt. I mean, you just, if this holds up, you just got the oldest relic by a factor of 10 to the 38, because the second oldest relic would be the helium and deuterium made when the universe was a second old, and you just broke the fossil record by a factor of 10. What do you think about that? What is that?
So I think, to me, one of the things that's really neat about this result is that we're probing the universe at a time when it was really, really energetic. So at an energy that is way bigger than anything we can ever make on Earth. So way bigger than you can ever make at the LHC by orders and orders of magnitude. And so if
how many orders of magnitude?
Well, the LHC is 10 to the 12, and this is 10 to the 25, so 13 orders of magnitude bigger in energy. And to me, you know, that's what hooked me. That's what made me get into this field. Is I said, well, if I want to probe physics at the highest energies possible, you know, I'm going to go out and look for this signal. And I think that that's to me one of the things that's really cool.
Yeah, actually, I'll just add a little bit to what Abby said, which is funny, is that the string theorists, who really are thinking really big, the origin of space, time, matter, and energy, the energies they're really interested in are just so far beyond the LHC that you can't ever imagine building such an accelerator. And so I call those the highest imaginable energies. It's called the Planck energy. And what's stunning is that these energies that you're probing are pretty darn close to that. So we're probing almost the highest energies that we've even imagined. Yep. And that's just stunning. Walt, do you want to add anything or a new thought here?
I think that's really exciting too. And it's the exciting thing to me is not so much just confirming that inflation happened. We already had a pretty good idea, I think many of us, that that was likely to be the case. But having a chance to figure out exactly how it happened, what it was that drove it, whether there were new particles and new fields that participated in it, and which of the many models could be correct. Inflation is a pretty big ballpark, and people have come up with a lot of inflationary models. And so at the same time you're talking about the cyclic universe being ruled out, most of the inflationary models also seem to have been ruled out because they predict that this signal would be too low for us to have seen. So it's not just a matter of getting a yes or a no, but having a chance to work out some of the really fine details. And that's what I am really excited to see in the next few years, is that the signal that we've seen is not just a detection of something detectable, it's a detection of something that's big enough that we can really hope to learn a lot about it.
Actually, I have to chime in on behalf of theorists here, because I mentioned earlier about the tension among theorists, that we didn't give you a good prediction, but we did set up something that Walt was just talking about, which is the highbrow theorists, the ones who were thinking about the most elegant theories, the string-motivated theories, were the ones saying, look, there's just no way that the signal can be detectable. It's just going to be way too small. And the lowbrow theorists who said, well, you know, maybe we ought to be a little more modest and just write down really simple theories, and maybe they're not well motivated, but they'll. Those were the ones that actually predicted that something might be detectable. So in the theoretical community, everyone's abuzz because you know. So we got a signal, that's good, but we shouldn't have gotten one because the really highbrow theories say it should be too small. So we got a surprise, and often in science that's the case. Is we like hints, but we also like surprises. Actually, you know, why don't we move on here a little bit? We'll just start roaming around. But this issue, this is really, really big, and let's come back to Carl Sagan and extraordinary results require extraordinary evidence. And so we heard a little bit about the Keck array, but of course, Abby, you're involved, and Walt's involved, and it's kind of the same people and a lot of the same detectors, and we wish you well. But you know, the two other experiments that I know of that have a big chance are the Planck satellite, which is doing the whole sky from space, and then there's some big telescope at the South Pole. Yeah, the South Pole telescope. And so why don't we? And then there's a sort of a wild one here, is that because this is all about gravity waves. Maybe we'll come back to this. Is there any way we could detect these with ordinary gravity wave detectors like the LIGO project? But let's. What about Planck and SPT? Are those, you know, when might we hear from those?
Well, I can tell you a little bit about the 10-meter South Pole telescope, and it is located right next door at the South Pole, which means it benefits from all those wonderful observing conditions, the dry sky and the ability to stare out through the galaxy at a very clear patch of the sky 24 hours a day. So we're going. We started a few years later in terms of integrating and on the sky. So we're working very hard to get down to these sensitivity levels. And hopefully confirm or whatever. Well, we're going to go and look at this and see what the data tells us. So that's happening. I don't know when that'll come out. We could actually think of confirming and cross-correlating very soon. We have that much sensitivity, but to do a totally independent observation is going to take a little bit yet. But we're not talking years. This is coming soon. And I don't know, maybe someone else wants to talk about Planck, or?
Right. So the Planck satellite is a European space mission that is has released its first maps last year, I guess it was, last March. But they have not released their polarization data. So their polarization data would allow them to, hopefully confirm this signal. And they're planning on their first release, I think, in October or November. So sometime in October or November, we ought to hear whether Planck has the sensitivity to see this small of a signal. And, we hope that they confirm.
And actually, the Planck is kind of an interesting wild card here, because if you look at, I guess it's called their blue book, their performance book. Their performance book would say that if the signal is as large as you think it is, they should be able to see it. But that brings us back to, you looked at a tiny patch of the sky, and so it could have just been especially loud there, and on the rest of the sky not as loud. Or of course, it could be that Planck, you publish a book about how well you think you can do, and you three know much better than I do. Sometimes you do better than that, and sometimes you don't do as well as that. And so I think everybody is wondering what Planck will say. In fact, Abby, the Friday before the big announcement, we had George Estathiou, who's one of the leaders of the Planck team, on the phone, and we were kind of talking about, none of us knew what the big announcement was going to be on Monday, just so in case any of Abby's collaborators are listening. She didn't leak anything, but people were wondering what it might be, and George didn't really tip his hand, did he?
No, Planck, as far as I can tell, has been pretty quiet, but they do plan to release, their first polarization results in the fall.
So you think they'll wait till the fall?
They've kept their cards close to their chest.
These analyses, especially for an all-sky measurement like Planck is doing, where they're not going real deep in one part, it's going to be hard. They're going to have to really understand their noise and their survey very, very well. So, we all hope they succeed, but they've got their work cut out for them.
That's right. Planck really has a different set of challenges than BICEP 2 or the Keck array, because our telescopes were designed from start to finish. The telescopes, the detectors, the observing strategy of just looking at one part of the sky, they were designed from start to finish just to go for this one science goal of finding this polarization signal from the gravitational waves of inflation. And Planck is trying to do a lot of things on the entire sky, looking at much smaller scales, looking at much bigger scales. And so in some ways they have a more complicated set of analysis problems to solve before they're ready to release their full results. So we do hope that they'll do very well, but that also means that whatever the sensitivity ends up being for B modes, they'll have a lot of interesting things to say about the galactic signals, the synchrotron and dust in polarization that's relevant for what we're doing will be measured much better by Planck than we've ever done before. And so Planck is going to have a lot to say, whatever the sensitivity ends up being for B modes. We're all pretty eagerly waiting for the fall to hear what they have.
So in terms of another CMB experiment confirming or giving us more information, I guess maybe in a few months we might have some more results from Keck, but again, not to extraordinary confirmation. You'd really want to see a different group using different apparatus. I know it's a different telescope, but the same detectors. We've got John and the South Pole Telescope that is working hard, and he says it won't be years. It'll be sooner than a year. And then we have Planck. Is there any other experiment that on the horizon that might be able to shed some light on this?
But there's a number of other experiments at various stages. mounted in the high deserts in Chile. And I don't really know where they're at. I think that they're a little bit lagging a little bit, but they're doing great. So in a number of years, if the signal is real that they detected, and as I said, it looks very good, and if the level is as high as they say, they need to just get a special spot in the sky, then we're going to start learning a lot about the signal. Not more than confirm it, but actually measure it very precisely and be able to go on from there.
So let me just come back, just as a theorist here. One of the remarkable things is these gravity waves that were made during inflation, if that's really what happened, are of all sizes, and the ones that we see on the world's biggest IMAX, the microwave background sky, are very, very big. And the LIGO and Virgo detectors, these gravity wave detectors that are looking for the collisions of black holes and the like, can detect gravity waves of much shorter wavelength, and which also should have been made during inflation. And there the devil is in the details, is, how does the strength vary with wavelength? Does it get stronger or does it get weaker? And, if you took your best guess, and that doesn't always work, you would say these LIGO and Virgo and even the space mission to detect gravity waves wouldn't really have a chance. But you don't really know. So that's kind of a long shot. In terms of detecting these gravitational waves directly by a very different technique. But let's suppose, so I bet, and I actually know this to be a fact, that you guys are thinking about new experiments, because once you've found the goose, so you now know that there's a goose out there. It's not just a wild goose chase. So let's go beyond confirmation. What do you want to measure next to learn more about what's going on?
Well, I'm happy to start. In fact, I mentioned there's a number of teams working in Chile, and of course we're at the South Pole with the 10-meter South Pole telescope in Keck and BICEP. We've actually all been talking about getting together to build kind of the next generation experiment. This would be a really big effort to go after this signal and characterize it. And we kind of put this collaboration loosely together and mapped out what we do before these results came out. And our strategy, kind of our guiding goal at that point, was make sure we go deep enough to get this signal or find out it's unmeasurable. So here we are in the middle of all of that, and the signal comes out to be as strong as it could possibly be without, in fact, even a little too strong, causing problems with other measurements perhaps. So we're kind of poised for this large community to go after this signal, measure it over the whole sky, and not just detect it, but as you said, measure how it scales with the wavelength of the perturbations. And that is, in other words, when you go to smaller scales, does the signal get smaller and smaller as you would predict? And does it do it at the right rate? Does it do it as predicted by these models of inflation? And that will tell us something, we hope, about how inflation actually started. What can we learn about physics at these extremely high energy scales? It'll also tell us whether these kind of local gravity wave detectors ever have a chance of measuring these signals.
So there's one fly in the ointment that I'm really curious about. So far we've been on a real roll in cosmology with the microwave background and dark energy and dark matter, and we have this picture that really seems to fit well. And in fact, often when you go to a conference and somebody shows all the data, this idea of cosmic inflation and dark energy, we call it lambda CDM, fits everything. And that's both good news and bad news. And when I look at this and ask, I'm not an expert on dust, but when I ask, what worries me the most about this result is that the BICEP team has detected it in the polarization of the microwave background. So that's a big, big signal. Well, it's not big, but it's a statistically significant signal. So no question that something is there. But theory also says that you should see it just in the temperature, the colored part of that picture. And what's sort of funny is John South Pole's telescope team published a paper, last summer, putting an upper limit on how big the gravity waves could be by looking for the signature not in the polarization but just in the variations in the temperature. And that upper limit is about a factor of 2 below what was detected. So, when we're polite, we call that tension. Others might call it a contradiction. The direction that I'm going here is maybe it's a crack in the cosmic egg, that we're seeing the gravity waves in the polarization, but not in the temperature, and so something. It's not wrong with the experiments. It's wrong with the theorists. Is that this lambda CDM thing is not perfect, and we've got a crack in the cosmic egg, and we need something else. What do you think about that?
Well, it might. There have been hints for a while now that maybe something else is going on, and with the Planck data, we see hints of things as well. If this is as high as it is, then maybe when we fit our data, we have to compensate it by allowing some new physics in there. Now that requires extremely strong confirmation before we will believe it. But that's the exciting. That's the crack in the egg is real exciting. It means maybe we have even more physics to learn. Maybe there's more neutrinos. Maybe they're more massive than we thought. Or maybe it's something none of us have thought of yet. So as an experimentalist especially, I think that's really exciting.
Yeah, and I think, to me, that's just the way science works. That's the process of science, is that you build an experiment that measures one thing, and you build a different experiment that measures a different signal. And then, you have to sort of modify your theories as you're going along. So if this really is a crack in the cosmic egg, how exciting, right? And that's the way that science works.
Now, there's some people who are less generous who, instead of using, I like the term crack in the cosmic egg, say, you guys have just been doing cycles and epicycles for the past 20 years. You've been dancing as fast as you can. When things don't fit, you invent dark matter, and then you invent dark energy. And now, I don't happen to subscribe to that, but
you're talking about the theorist, huh?
Well, I am a little bit. That we seem to be converging on a picture. This idea of inflation, and at first blush, what this says is this. I mean, I think everybody's using this term now. Smoking gun. This is the ripples in space-time that were created during inflation that got stretched into reality by the tremendous expansion of inflation. So we have a very nice little picture. Now, we haven't gotten our heads around the picture, but maybe there's something, maybe we're just way off base. I don't think so, but maybe we are.
It could be, but I have to admit that, as experimentalists, I went into this whole field thinking, let's just see what's there. There's all these crazy theorist models out there. They can generate models at a furious rate. Let's just see what's there. And it's been just remarkable. The cosmic microwave background observations in particular are right on the money with these theoretical predictions of what we should see. The parameters we adjust to make them fit, but the parameters are not new physics. They're just parts of the model. So it's all looking good, but I for one think it'd be great to find this crack and explore it. And that's where the new insights, that's where the new physics will come from.
So as we go along, for those of you out there listening to us, I actually am looking at your questions and trying to work them in to this conversation. And the one question here that we touched upon very lightly that's so mind-blowing about this is gravitational waves. If we did a hangout just talking about gravitational waves, that's going to warp that's going to stretch everyone's mind. These gravitational waves are ripples in space-time predicted by Einstein, and just like electromagnetic waves, they come in different colors or wavelengths. And so just like electromagnetic waves, some electromagnetic waves you can detect with your human eye. Some take a radio receiver, and so these gravitational waves. What's stunning about it is, if this is really true, the gravitational waves here that were detected have wavelengths millions of light years, actually billions of light years. But I didn't want to scare people. And then you know, the LIGO detector is working at the other end, looking for gravitational waves whose wavelengths are more like kilometers, and cause two particles, two mirrors, to move apart and close together by a tiny amount. And so just forget about the cosmology part, just the gravitational wave part is amazing. And then it's been pointed out by people that you know, if it's really what we think it is, this is showing that the metric of space-time, Einstein's theory, is a theory that didn't have quantum mechanics in it, that his space-time actually is subject to quantum mechanics, and that's also amazing. So this is, yeah, how big is this? I think this is bigger than the Higgs. Walt, what do you think? How big is this discovery?
You just said they're billions of light years long.
That's true. What you just said, Mike, is one of the things that really excites me the most, is just looking at that map and seeing that each of the blue and red spots is not just a imprint of a gravitational wave. It's actually an imprint of a quantum fluctuation of the quantum gravitational field, or the graviton field, that existed as inflation was happening and got stretched out to be these billions of light years long. And this is something that we've been kind of looking for a hint of for decades. Even back in Einstein's lifetime, he was trying to find ways to put general relativity together with what we know about the other forces and combine them into one theory of everything. And people have come up with string theory and with many other ideas for how you can go about that. And it's really exciting to me just that maybe this is the first crack at evidence for which of those ideas can be right, which ones can be wrong. And so every time I look at that map, that's what I'm thinking about. That these are every blue and red spot is quantum gravity.
You know, another way to think of it, how big it is, at least to some people, is, you know, the leaders of this BICEP group. 10 years ago, even more than that, you know, John Kovac, Clem Pryke, and Jamie Bach, and Xiaolin Pu, they dedicated themselves to this experiment and poured everything into it, and this is the one thing it can do. It was worth it to them, even though, as you say, the prediction from many, many people was it was unmeasurable. But they felt that it was just so important to look and check because the implications would be so profound that they went for it and dedicated. So I think it's huge. Quantum gravity, energy at enormous scales, smoking gun of inflation. It's hard to downplay any of that. It's amazing.
Abby, you want to weigh in before we wrap up here?
Yeah, I mean, I think it's a funny thing when you're sort of on the inside of of a discovery like this, right? For a year, the whole collaboration was talking about this discovery as if it was sort of just numbers on a little bit in a very business-like fashion, right? Because we wanted to make sure that our result was the best it could be and do all the checks that we needed to do, and we did it in a sort of very business-like fashion. And it's only when you release the results to the world and watch the reaction of the community that, at least for me, that it sort of hit home how important it is, right? That I got a question at a colloquium that was, you know, which do you think is the most important? Is it discovering inflation, discovering quantum gravity, or discovering gravitational waves? You know, and it's a sort of meant in humor question, but how do you know, there's no way to downplay that, right? I mean, if it is what we think it is, it's a very big deal.
So I think it's time to wrap this up, and so I want to, this has just been terrific fun, and thank you, John and Walt and Abby. I hope you had as much fun as I did today, and I want to thank the viewers for who joined us and sent in their questions, which we did our best to try to work the answers in. I hope what you take away from this today is this is so big that we haven't figured out how big it is. And I want to come back to this 10 to the 38 number because we, you know, actually if I say 10 to the positive 38, so this fossil, our oldest fossil before came from 1 second after the Big Bang, which is just mind-boggling that you would even know anything about the universe then, when it was a soup of neutrons and protons. And this one is taking us back 38 orders of magnitude earlier in time. And I can't think of an example in science where we had such a leap of 38 orders of magnitude. And when you just try to wrap your head around this, that we're talking about the universe. I mean, I'm a theorist. For all my career, you know, I go up to the blackboard and we create universes and talk about them when they're really, really young. But we now have some evidence. We have something that came to us when the universe was, at least we think we do, when it was 10 to the minus 38 seconds old. And so if we sound a little bit confused today, if we sound like we don't have our heads totally wrapped around this, I think it's because this is so big we haven't really fully understood the implications. And of course, I think all of us are just the tiniest little bit nervous that maybe this is too good to be true. I mean, you know, maybe it's certainly quacking like the polarization that we wanted. So it quacks like a duck, but is it really a duck? So we're going to hear a lot more about this. I predict that BICEP is going to go to the lexiconic stratosphere, right up there with Higgs, so that if you're a cosmologist and you get in a cab and say you're a cosmologist, the cab driver is going to ask you, tell me about that BICEP thing, which is what happened after the Higgs. And so finally, if you want to see this webcast again or share it with your friends, it's going to be available on the Kavli Foundation website and on YouTube. And if you want to ask questions, Twitter to @Kavli Foundation. So thank you again for watching. We've had a great time, and you know, cosmologists are just having a ball with this new discovery. So thank you all.
Yeah, it's been fun.
Thank you.